Neural Networks workshop where we're going to be building and training your very own neural network in Python. We're going to spell out everything you need to know so that you get a very intuitive knowledge of how this piece of technology works. We're going to do it from scratch with no libraries at all, right? My name is Kalya. So it is based on a video that was released by Andrej Karpathy. If you don't know who that guy is, he is the leader of AI at Tesla. He made a video where he essentially created a neural network completely from scratch, posted a video on it. This presentation is going to be going through that in my own interpretation of it, right? So we show all the concepts that you need to understand so that you can get a very fundamental and intuitive understanding for it. So the very first question that I want us to tackle is, what is a neural network, right? Specifically in the context of machine learning. Because we know neural networks come from biology, how do these two concepts relate to each other, right? The understanding that I want each and every one of you to start developing here is that a neural network really just is a function, right? Like from mathematics, right? Now, this isn't a very satisfying answer, of course. There's much more complexity above and underneath that concept. But at the end of the day, that's all it is. A neural network is just a function, right? And a first question that you might have upon reading that statement is, okay, well, what is it a function of, right? What are the inputs and outputs of this function, right? And really what we want to do is we want to get the understanding that a neural network is just like functions that we know, right? A function of x named f, which outputs one value, just a polynomial, right? Even functions that have multiple inputs and output multiple values, right? Could we potentially understand neural networks in the same way that we understand these functions right here, right? So, how do we answer this question, right? What is a neural network a function of? What does it output, right? If it is a function. Well, to answer this question, what we're going to do is we're going to explore how to build neural networks, right? And the first step in that is tackling what neurons are, right? Neural networks, neurons. What is a neuron, right? If you ask this question to a biologist, he might point you to this illustration right here, right? We have dendrites, which are these structures over here, which are essentially input signals to the neuron. And then we have the axon, which is like the output of the neuron, right? So electrical signals flow in from presumably other neurons. Then the axon outputs a new electrical signal based on some understanding of which electrical signals in the input are more important for the output, right? So, in machine learning, what is a neuron? As it turns out, what we do is we create a mathematical model of this biological system, right? And by that, I really just mean a way to use math to describe this biological system, a neuron, right? So a neuron is a mathematical model of a biological neuron. It uses math to describe this system. How does it do that? It's a function. So let's write that function, okay? A neuron really just has inputs and an output, right? We're going to represent the neuron with green over here. And then we have inputs, which really are just numbers, right? What we do in neurons is that we pair each input with a respective weight, which is a value that ranges from -1 to 1, right? We multiply each input with a respective weight, right? So like this. We could say that this right here is input x1, x2, x3. This right here is weight 1, weight 2, weight 3. And so what we do is we take each input, x1, and multiply it with w1. And then we add to that x2 multiplied by w2, right? Or w2, not w3. What this is trying to simulate is, well, remember, in the biological neuron, what we do is we take in input electrical signals, and we try to give an importance to each signal. This is exactly what the weights are doing over here, right? We're taking each input and we're multiplying with a weight, and this weight is a value from -1 to 1. Sort of give us like an importance, right? Maybe the smaller the value, the less important the input is, right? Once we make this weighted sum of our inputs, what we do next is that we add on top of it a special value, which I'm going to draw here in orange, which we call the bias, right? What the bias is going to be is sort of like a way for us to control the function of this neuron independent of any inputs, right? maybe we want this neuron to be very trigger happy. Maybe we want it to always output something large independent of the inputs that we give it. So this is why we have the bias. Again, it's also a value that ranges from -1 to 1. The final step in all of this process is we take this weighted sum, which we put the bias on top, and we pass it through the so-called activation function. What this activation function does is it makes sure that our output always is between -1 to 1. Usually we use something like 10H, so 10H graph. As you can see right here, this is a graph of a sigmoid, right? So very negative values become squashed to 1, no matter how negative they are. Very positive values become squashed to 1. Did I say that right? Negative values to -1, positive values to 1. Does that make sense? Is that good? Here's just I guess a better diagram. So once again, inputs, multiply with each one of the weights, put that on top of that the bias, pass everything through an activation function. That is what a neuron is. That is the basic component of a neural network, right? So, yeah, just before we get started with coding, this right here is dimensionality, right? And so when I say dimensionality, I want you to think of the number of inputs that a neuron has, right? Because over here I drew it with 3 inputs, but who says we need 3 inputs? We can do how many inputs we want. We just need to have enough weights for them, right? 3D, 5D, 10D neurons. Does that make sense? So, as Andrej would say, code is truth. So let's get ready to code. I'm just going to ask you guys to create a py file. It's going to be neuron.py, and we're going to be coding this neuron right now live. This is the kind of behavior that I want. In some main.py file, I want to import this neuron class, right? I want to determine the dimensionality of this neuron, and I want to create a neuron object. Then let's say I have some set of inputs, 1, 2, 3. I want to be able to call this neuron giving its inputs, obtaining our output, right? Let's code that right now. So if I come over here, this is right here is my folder. This is bash. So I can create a file by just running touch main.py. So as you can see, I have main.py file over there. We can code it right now. And I'm saying that from neuron, I want to import a neuron class. I want to make the dimensionality equals to 3. I want to create a new neuron with dimensionality is equals to the dimensionality that we set. Then I want to create an array of inputs, 1, 2, 3. I want to get an output, which is just going to be calling our neuron, passing in our inputs. And I want to print this output, right? So that is the behavior that I want in main.py. Okay? What we're going to do next is we're going to create over here our neuron.py file. So in neuron.py, we're first going to be importing NumPy, because remember, weights and biases are from -1 to 1. So we need to be able to generate random numbers between -1 to 1. So import NumPy as np. I think it's np.random.seed is equals to 42. This right here is just essentially removing the randomness. So just put this and you should get the exact same values that I'm using. Okay? And then we're going to create this class neuron, right? We're going to define the init method of this neuron, which takes in, well, first of all, it takes itself, of course. And we also need to take in the dimensionality, right? Because remember, here in main.py, we have the dimensionality that we give to each neuron, right? And so what we're going to do is every neuron has weights, right? So let's make that self.weights is going to be equals to a list. I'm going to put something in that list in just a bit. Every neuron has a bias. Every neuron has an activation function. Okay? So weights are just going to be, remember, random values between -1 to 1. How many random values? Well, the dimensionality tells us that, right? That's the number of weights that we need for each one of our inputs. So we're going to say np random.uniform -1 to 1. This essentially generates a random value between -1 to 1. For how many times? Let me just close this right here. So np.random.uniform for how many ever times the dimensionality is, right? So here we have a list of weights, just random numbers. The bias is going to be just one random number, so we don't need to make that list. We can just say random.uniform 1 to 1. And the activation function is going to be 10H, all right? So that right there is all the data that our neuron has. If you have any questions at any point, just stop me and ask, alright? Then we're going to define this special call method, which in Python allows us to take in, to do exactly the behavior that we had in main.py, right? Remember, in main.py, we call the neuron on a set of inputs. So we're going to define that method right now. This is essentially the same thing as doing call on I, right? It's just a special Python syntax for us to do this. So we go over here to neuron. Call is going to be taken in itself, and a set of inputs on which we want to generate the output. And right now, we need to return that expression, right? Remember, if we go over here, we wanted this expression right here, right? That is what we want out to return. So how do we achieve this? Well, self.f, and then over here we're going to do a sum, and hopefully this is going to be a bit clearer now. Sum, once again, just our list, x sims w for x and w, and zip. This is just a bit of a nicer formatting, I guess. That's going to help us really visualize things a bit clearer. I think this is better now for us to understand. So we do our weighted sum of our inputs, we add on top of the bias, add all of that up, pass it through the activation function, right? So hopefully this is all that we need to make this neuron work. Let's see if this works out. So I'm just going to run next shell because I need to get all my Python dependencies. This is specific to my OS, but just make sure that you do like a pip install numpy. Make sure that you have numpy to run this. And right now, if I have not made any mistakes, if I run Python main, there we go. So what just happened, right? Well, we have our main.py file. We just gave the inputs to our neuron, and we printed the output, right? And notice that over here, our inputs are quite high. Remember our 10h function, right? Our 10h function just squashes all very high inputs close to 1. So that's why we expect our neuron to output something that is very close to 1, right? So that is the first building block to neural networks, right? So we're able to make neurons like this. We're trying to understand how to build neural networks so that we can understand that question, right? What is a neural network a function of? What does it output, right? So the first step of that process is done. Neural network, neuron, we know what a neuron is. But what about the network part, right? In what sense are neurons connected to each other? That's the question that I want us to tackle now. So what are networks of neurons, right? That is the next step that we want to be tackling, right? And to answer this, we're going to explore how to chain neurons together, right? I was going to do a visual demonstration of all this, but I'm just going to show the illustrations because I think this is going to be a bit quicker. So, a layer of neurons, right? This is a new concept that we're going to be introducing right now. What is a layer of neurons, right? Every layer of neurons is defined by two things. First of all, how many neurons in that layer? That is the first thing that we define. And then the dimensionality of each one of our neurons, right? As you can see right here, over here we have a 3D layer because every single neuron in this layer has 3 inputs. And we have 4 neurons in this layer, right? So we can give 3 inputs to this layer. And what does it mean to give 3 inputs to this layer? It means that we give those 3 inputs equally for every single one of our neurons, right? So we feed input 1 into the first weight of the first neuron, into the first weight of the second neuron, into the first weight of the third neuron, and then the second input into the second input of the first neuron, and so on. So we just pair up all those inputs with the weights, all right? We're going to be coding this too, right? This is the behavior that we want. So I'm going to make some slight changes to main.py. We're not going to be porting neuron. We're not going to be creating a neuron anymore. We're going to be creating a layer. So I want you to define a layer.py file from which I can import a layer class. I want you to define the dimensionality of my layer. I want you to define the number of neurons in my layer. And I want you to create a new layer object by just using that class. Then same thing again. We have a set of inputs. We give those inputs to our layer, and we print the output, right? That's going to be the next step that we're going to be coding in here. So let me make those changes to main.py file right now. So we're going to go to main.py. Again, we're not going to be doing any neuron anymore. We're going to say from layer, import the layer class. And again, we have not created this layer.py file, but we're going to be creating it in a bit. So we have the dimensionality. We want a number of neurons. I think I did 4 in the slides if I am not mistaken. Yeah, 4. So we're going to do 4. I want to say that L is equals to layer. We pass in the dimensionality and the number of neurons that we want. And then we just change this. So this right here is the kind of behavior that we want. Very similar to what we had before, but now we're doing it later. So let's create that layer.py file. Let me just make sure that this is correct. Yeah, this should be alright. So let's create that layer.py file. Come over here, layer.py. There we go. So this right here. So our layer uses neurons, so let's import neurons first step. So from neuron, import a neuron. Then we're going to create a new class called layer. We're going to define its init method. And remember, what does every layer need? Well, besides self, dimensionality, number of neurons. Alright? Then every layer has what? Has a list of neurons. So self.neurons is going to be equals to a list. How many neurons are we going to be creating? Well, the number of neurons input argument tells us that. So for a range of n. So this right here gives us our neurons of our layer. Then we're going to define the call method. Same thing that we had before. Define call. Like this. Takes in self, takes in a number of inputs. It's pretty similar to the code that we had before, but now it's going to be returning a list of n on those x inputs for n in self.neurons. Right? And that should be pretty good. Let me see if I made any mistakes over here. Always cautious of making mistakes live, but it just happens with live demos. But this should be alright. So right now, remember, this is what main looks like. So if we just run this, what do we expect to get? Our layer has how many neurons? 4 neurons. We're giving it 3 inputs to each neuron, and we're expecting 4 outputs, right? Because we have 4 neurons, 4 outputs. So if I run all of this code right now, python main.py, alright. So now we have our 4. Oh, it's quite low in the terminal, isn't it? Let me just put that up. Our 4 outputs. So that is what a layer is, right? Next step is we want to make sure that we connect layers to each other. And for this, we're going to need to make sure we understand one principle to connect layers, right? Yeah, we code a layer. So when we are connecting layers, what we want to do is, let's say that we have a layer L, 0, 1, 2, 3, 4, right? Or 0, 1, 2, 3. We have 4 layers over here, index 0, 1, 2, 3. For index layer L, we want to make sure that the dimensionality of the neurons in that layer matches the number of neurons in the previous layer, right? And it's good to stop and ponder on why this behavior might be, right? Can anyone tell me why this behavior makes sense? Why we are matching the dimensionality of a neuron, of neurons in one layer with the number of neurons in the previous layer, right? Does anyone have any idea why this might be? Each layer is going to be outputting a certain number of values, which is the number of neurons. And remember, the neurons from another layer are going to have to take exactly that number of outputs, right? So look here, the first layer has 2 neurons, it outputs 2 values, right? It wouldn't make sense for the neurons in the second layer to have 3 inputs, because we don't have 3 inputs to give them. We only have 2 outputs, right? So that's why we need to match the dimensionality of neurons in a certain layer with the number of neurons in the previous layer, right? This is going to look a little bit messy in code, but that's the principle, right? It's not that complicated once you write it with words. So this structure right here, I didn't even mention this, but it probably should. It's called an MLP, which is a misnomer, by the way. It's called a multi-layered perceptron. It's just the vanilla version of neural networks. We also call them fully connected neural networks, all right? So we're going to be coding this, and it's going to look pretty similar to the behavior in main.py. I'm just going to create an mlp.py file. I'm going to import from it MLP. Then the inputs that we give to create a new MLP are going to be different. I'm going to define the number of inputs for the first layer only, all right? Because over here, remember, we are inputting 3 things. And then I'm going to define the number of neurons in each layer. Why am I not defining the dimensionality of each layer? Because of this principle that we just discussed about, right? The dimensionality of each layer is going to be taken care of for us because we're going to be applying this principle in code. So we don't need to specify that. No, we specify the number of neurons in each layer. Sound good? So this right here is the behavior that we want. Let me modify that in main.py right now. So go over here to main.py. We're not talking about layers anymore. We're talking about the real thing, which is multi-layered perceptrons. Number of inputs is equals to 3. I need to define the number of neurons in each layer. Completely arbitrary. You could do whatever you want. I'm going to do 2, 4, 4, 2. Then I'm going to say that my MLP is equals to MLP. Number of inputs and enums, right? And then, if I'm not mistaken, this is pretty much it. And then we need to change this to MLP. From LP, import LP, number of inputs, number of neurons in each layer, create MLP, and then give the MLP the inputs, right? What do we expect this output to be? Quick question, right? Remember, the last layer in our MLP has 2 neurons, right? So we expect the output to be 2 different values. Sound good? Let's create mlp.py. So let's come over here, mlp.py. We're going to be importing layers because we need layers. So from layer, import the layer class that we have just defined. We're going to say class MLP. I'm going to have to define here the inputs. So def the init method, self. Hopefully I don't make any mistakes this time around either. So we have the number of inputs, and we have the number of neurons, right? So every MLP is going to have just simply a layers array, all right? So self.layers is going to be a new array. And so we're going to say layer, and every layer needs what? Dimensionality of the neurons in that layer, and the number of neurons in that layer. For D and N, and now this part is going to look a little bit weird because we're going to be applying exactly that principle that we just talked about, this principle right here. All right? So we're going to be doing essentially a zip of 2 different arrays. If we just come over here, the first array is going to look like this. We're going to get all elements but the last element of the concatenation of the number of inputs plus the number of neurons and just simply the number of neurons, all right? So again, this might look a bit messy, but all it's doing is just applying that principle of matching the dimensionality of number of neurons in one layer with the number of neurons in the previous layer, right? Notice right here that we're just giving each layer a dimensionality and a number of neurons. The dimensionality is always going to be this number right here, right? And so notice that the first element of this array is the number of inputs. That makes sense. We want the dimensionality of our first layer to be the number of inputs that we give to the MLP, right? And then we want the number of neurons of that layer to just be the numbers that we specified in our input, right? Then the dimensionality of the second layer should be the number of neurons in the first layer. So we just append on that entire list over here. All right? So that is how we create the layers of our neuron, and we take care of dimensionality automatically. We don't need to do that. Sound good? Next, we're going to do the call method, because remember in main.py, we're calling our MLP. So we need to define that method right now. Go to File, Call Method. Takes in self, takes in a number of inputs. And what we're going to be doing over here essentially is we're going to say that x is equals to our inputs. And then for each layer that we have, so for L in self.layers, we're going to say that our input is going to be equals to, essentially we're going to be taking our latest input and we're going to be passing it through our layer and then saving that in that same variable, right? So this right here takes in our XS, our initial inputs, passes it through the first layer, then passes it through the second layer, then the third layer, then the fourth layer, right? So by the end of that process, we just want to return this X value. That's all we want to do. Let's see if I made any mistakes again. Hopefully not. Hey, there we go. So running the code, this right here is our neural network, right? It's outputting our values that we expected it, given the inputs of 1, 2, 3. If I wanted to, I could change the inputs to whatever I wanted, honestly. I could just do, I don't know, 1, 0, 3. That might change the outputs, I'm pretty sure. So yeah, different outputs for different kinds of inputs. Actually, they look pretty similar here right now, so maybe that's something of the weights. But yeah, that's it. that's a neural network constructed. All right. So once again, this right here is the code for the MLP. So we asked what are networks of neurons. We said we were going to explore how to chain neurons to create networks to answer this question, and we have done that now. We have created the MLP class, right? So these right here are networks of neurons, essentially, right? And so let's go back to the first question, right? We said that a neural network is just a function of what? And what does it output, right? We are now in a good position to answer these two questions. So let's answer the first part of the question. What is a neural network a function of? Recall, from main.py, we have our set of inputs, and we give it to our MLP, right? We can really just rephrase this as giving variables to our MLP, right? So we're giving an x, and y, and a z. So it really allows us to do that formulation. Because remember, we wanted to answer this question in such a way that we start to understand neural networks in the same way that we understand those purple example functions that I had in the beginning, right? These ones were here. We want something like this, and now we can actually do it, right? So go back to that slide. Where is it? There we go. So that allows us to say that our MLP is a function of x, y, z, right? Arbitrary inputs. Now, the second part of that question, right? What does it output? Once again, remember, we can rephrase this right here into this, right? Remember, doing this syntax right here in Python is just calling the call method of the class. And we have defined that method. Also remember that in our example, our MLP has a very specific structure, right? We gave it that structure. Using all that knowledge, could we potentially find an expression for the MLP? Yeah, you can. So this is it. This is literally the entire function. It looks a bit silly. It was very silly to do. It took me 3 hours to write it. But that's it. That's the MLP. Alright? So remember, we asked what is a machine learning's neural network. It's just a function. What is it a function of? What does it output? And we got those answers, right? If you didn't get much from this section, all that I want you to understand right now is this. A neural network is just a function of an arbitrary number of inputs to an arbitrary number of outputs, right? Still though, you look at these answers and you're like, yeah, okay, that's a neural network, that's cool. X, Y, Z outputs that huge expression. Were these really the answers that we wanted? Are we satisfied with this? Right? Where is the intuition in all of these answers that we got, right? And this is part of a broader question, which is, what does a neural network actually do, right? We know what they are. What do they do? Make sense? So, to answer this question, what do neural networks actually do, what we're going to do is we're going to try and find some intuition behind these mathematical expressions, right? And to do that, we're going to have to go back to basics and rethink, what do neurons and what do layers actually do, right? So, the second idea, the new concept that I want us to start understanding right here is, we want to go from a picture in the left where we see neurons as just, weights, inputs, bias, activation function, output. We want to go from this picture to start looking at neurons as really just a way to generate representations of something based on input representations, right? So there exists some object. It can be anything you want. It can be the weather. It can be an image. It can be, I don't know, pictures of cats and dogs like people usually do in neural networks, right? Our inputs somehow represent this initial object. What does a neural do with those representations? Takes them, uses the biases, or just a bias I should say, uses the weights, uses the activation function, and generates a new representation of that initial object that we had, right? Same thing happens with layers, alright? We have this picture of layers right here, which is just numbers flowing from neurons to neurons. What we want to understand is that at the end of each layer, we have a collection of values which together are a representation of this initial object, right? Such that at the very end of our neural network, we have values that are representation of that initial object. Does that make sense to everyone? Yeah? So, what do these representations actually look like? They are numbers, right? Well, they're actually completely random. So, remember, in our neural.py file, we had those weights. They're random values, completely random, except the activation function, of course. But these representations are just random numbers right now. In fact, this is what we get from main.py, right? So, where is the intuition behind all these answers right here, right? We said we were going to rethink how neurons and layers work, which we have done right now, right? The intuition is in the fact that neurons and layers, all they really do is create representations. They're random right now, but they are representations. That's the intuition that I want you to be having about neural networks, right? So, okay, yeah, these representations are random. What if they were not, right? What if we could take these representations and make them actually useful, right? Say that we had input data about the weather to a neuron, right? We have humidity, we have temperature, we have cloudiness. What if we could tweak the weights and biases of our neurons such that the output is the chance of rain, right? We can change those values. They don't need to be random, right? We can just change them. Same thing happens for layers, right? Imagine that you have the pixel RGB values of a picture of a hand-drawn digit, right? Like I was drawing right now in Excalibur, right? I could give those pixel RGB values, which are a representation of the hand-drawn digit, and maybe by the end of the network, I have 10 outputs. First output is the chance of that hand-drawn digit being a 1. The second output is a 2. And I could manually tweak all those weights and biases to achieve that task. Is that feasible? Does anyone actually tweak billions of parameters by hand? No, we don't do it manually, right? No, we want neural networks to do that by themselves. So, what if we could automatically control those weights and biases, generating intentional representations, not random ones, right? This is why we train neural networks, right? We want our neural networks to learn how to control their own parameters such they generate intentional representations, right? We want a set of red inputs to give a purple output, but our neural network is currently giving not quite the purple output that we want. The colors don't actually look that great on the board, but I swear they look much better here. So we want the neural network to change its own biases and weights such that they learn to output the things that we want. Okay? That is what neural networks do. That is more intuitive. That is a better understanding of what neural networks are. Alright? So they learn to output what we want by being trained on inputs and their desired outputs. Okay? How do we train neural networks? How does that process actually work, right? And I just wrote like here 5 simple steps that essentially tells us how this all works. So, in a neural network, we essentially collect data that represents anything really, right? Like we have with the weather, like we have with the hand-drawn digits. We generate inputs. Then what do? We pair up those inputs with what we desire the network to output given those inputs. We generate so-called ground truth outputs. Then what do? We take those inputs and we give them to the neural network and we see what the neural network is actually doing, right? What is it actually outputting us? These give us predicted outputs. We calculate the difference between the outputs that we actually want, the ground truth outputs, and the predicted outputs. And then what we want to do is we want to slightly change each weight and bias automatically of our neural network such that we reduce that difference, right? In that sense, our neural network is kind of like learning to output what we want. That makes sense? And then we reprieve from tree, right? We collect, because we only slightly change our parameters, so we only slightly reduce that difference. We want to be repeating this over and over. So once again, slightly change parameters. See what our neural network is outputting now. Compare that to what we want. Change parameters. See what it's outputting now. Change parameters. Keep repeating over and over and over, right? Which is why you need a lot of compute in AI. There's a lot of parameters that you need to do. Alright? So, first step in that process, we want to calculate the difference between the ground truth outputs and the predicted outputs. How could we possibly achieve this? Right? The concept that I want us to introduce here, maybe you've heard of it. It's called loss, right? So loss is going to be a singular value that characterizes how well or how bad our neural network is doing, right? Greater the loss, worse it is doing, essentially, all right? So loss is just really going to be our difference. How do we get loss? We create a loss function, right? Our loss function takes in our predicted outputs and our ground truth outputs, and it outputs this value that we want, our loss. So let's update main.py to kind of like be the behavior that we actually want, all right? So we had the same LOP structure as before. Now our inputs are the same, but we now have ground truth outputs, right? Neural network outputs 2 things. What do I want it to output when I give it 1, 2, 3? 1, -1. Is it actually doing that right now? No, but it's fine. We're going to make it learn, okay? Then we get our predicted outputs by giving our MLP our inputs. We set our loss function. I'm not going to go into this right now because you don't know what SSE is, but we're going to be doing it in just a second. We get our loss by giving the loss function our predicted outputs and the ground truth outputs, and we just print our loss. For now, that's the behavior that I want us to be achieving. Let's go to made up UI and do that right now. So GTO is equals to 1, -1. What else do I need over here? Alright, I need the predicted outputs, which is just giving our MLP our inputs. I want you from loss import a specific loss function, which we're going to get into right now. I want you to set our loss function to be exactly that. And then I want our loss to be, right, we need to make our loss get the output of this loss function. And this loss function, we're going to be giving it the predicted outputs and the ground truth outputs. Alright? And we're going to print our loss. Is that pretty much all that I wanted to have for this part of the workshop? I think so. Alright, sound good. So that is behavior that we want. Now we need to code that SSC loss function. What does it actually look like? We're going to do that in loss.py, a different file. Okay? So, loss.py, we're going to define SSE, which is going to be taken in predicted and ground truth outputs. Now let me just make sure I don't mess this up again, because I do have a habit of doing that. Where is that going to be located at? It's going to be located over here. Alright, cool. So, what SSE actually looks like, I'm going to use the slides for this one because it's going to be easier. So, this right here is a basic loss function that we're going to be using right now for the workshop, alright? It's known as the sum of squared errors, right? For each prediction and each ground truth we have, subtract them, square, add all of the square differences. Simplest version of loss you could possibly have in a neural network, right? And I kind of already have the code over there, so I'm just going to copy it because it's going to be a quicker. But it's essentially the same thing that we're doing right here in this formula, right? Predicted ground truth square for P and GT and PO GTO. Alright? Let me just copy this real quick. Leader, that, paste, delete that. So that is our loss function. So if I've not made any mistakes right now, when I run main.py, what do I expect to see? The loss of our neural network, how badly it is doing. Okay? So Python main.py. There we go, 4.26. You might ask yourself, is this a good loss? It's terrible. It's very bad. Usually we want our loss to be like 0.0 something. Right? This right here is terrible loss. Which really just means that our neural network is not doing well right now. And we can actually see that, right? If I go over to main, and I print the predicted outputs, honestly, like this. So you see the predicted outputs are negative 0.92 and -2, right? So almost -1 and -0.2. Remember, what are the ground truth outputs for this neural network? We wanted to output 1 and -1. So it's kind of like the first output is like the polar opposite of what we want right now. Not good at all. But our loss is indicating that to us. We know that our loss is very high, we need to reduce it. Okay? So, we now know how to calculate the difference between our ground truth outputs and the predictions. That's the loss function. Okay? The second step in those 5 or 6 steps in training neural networks, right? We now want to slightly change our parameters in such a way that we can reduce this difference, this loss that we have right here, right? How could we achieve this? So the insight right here is, first of all, to understand that our loss function is a function of our parameters of our neural network. Alright? Remember, this right here is main.py. We have our inputs, our predicted output. We have the ground truth. And look, our loss function is a function of our predicted output, which in and of itself is a function of our MLP, a function of all the parameters, right? We can essentially write this. Our loss is the sum of squared errors of the MLP given x, y, z, and our ground truth outputs, right? So loss is just a function of all of our parameters. X, Y, Z, the first weight of the 0 neuron of the 0 layer, the 0 weight of the 0 neuron of the first layer. Anyways, all the way to bias. There's a bunch of parameters over here. I think that for the network that we created, there's like 50 parameters. And then the ground truth, all that. Also recall that we have the code for the sum of squared errors, right? using all this knowledge, could we write an expression for our loss function, right? Yeah, you can do it. This one took less time, took like 25 minutes, because I already had all the other things. So this right here is our loss function, right? It is a function of all of our parameters, right? That is the first insight to understanding how we slightly change parameters to reduce our loss. The first thing you need to understand. Loss function is a function of the parameters in our neural network. All right? We still cannot answer this, so we need more insights. Okay? So, if we could find the influence of each weight and each bias in our loss, then we could use that knowledge of how each one of our parameters influences our loss to slightly change those parameters, thus reducing the loss. All right? And notice that the influence of each weight and each bias in our loss kind of sounds like we're saying we want to know the influence of variables in a function. And when I say the influence of variables in a function, I want you to think immediately of derivatives. All right? Let's see if you guys were paying attention to calculus 1. I assume you guys all are. You guys are probably smart. So quickly pop quiz. What is the derivative of that with respect to 3? Anyone? Quick arithmetic?
6x
minus 7. Alright, so 6x minus 7, and then we plug in 3, we get 11, right? So I asked the question, what is the derivative of that polynomial with respect to x at x equals 3? And you go ahead and tell me this. I just realized that there's like a little, should be like a prime over here, just ignore that. Is that really the answer that we want? I'm going to ask again. No, really. What is the derivative of this function with respect to x at x equals 3, right? You just told me it is 11, but is that really the knowledge that we get from derivatives, right? To understand this question more deeply, let's go back to the definition of derivatives in the limit. You should all probably remember this formula, right? Derivative is the limit as h equals to 0. You take in the f of x, add in that h minus the other x divided by h, right? So what this formula is actually telling us is that a derivative of a function of x with respect to x at a certain x value is really just a measure of how much f changes if you slightly nudge x in a positive direction, right? The derivative is just instantaneous rate of change. All right? So, we can immediately apply this knowledge to change variables in a function such that we reduce that function. All right? Take a look at this example right here. We want to find the derivative of each variable in a function with respect to that function and slightly change each variable, slightly reducing that function. All right? What does that actually look like? Here's a very simple example in code of what I'm trying to show. All right? So we define a function of x. Right here, the same function that we had before. We're interested at x equals 3, our derivative. Here is just an approximation of the derivative, right? Remember, we want to take h as it goes infinitely to 0, but honestly, if we just use this value, it's going to be good enough. It's going to be a good approximation, okay? So we find the gradient, essentially the derivative of x at x equals 3 of f, all right? And then what do? We slightly nudge x in the positive direction of that gradient, right? We have this LR right here, which if you know a bit of AI, you know what this is, but for now it's just going to be a small value, right? So we use the knowledge of the derivative to slightly increase x in the opposite direction from which x increases f, right? So what this right here is actually doing, right? We're using derivatives to decrease f by slightly nudging x, right? Before our f was 16, once we slightly increase x in the positive direction of our gradient, we reduce f, all right? So that is the simplest example of what we can do with derivatives. We can get a bit more complex. We can do a function of multiple inputs, right? That g function that we had before. I'm just going to make it output one variable this time, so just that. So say we're interested in the derivative of g with respect to a, with respect to b, with respect to c at a equals 1, b equals 2, c equals 3, right? We can calculate those gradients in the same way that we did before, right? Notice that for a grad, we only increase a, right? For b grad, we only increase b, right? And then we can use that knowledge to essentially decrease g, right? We slightly nudge each parameter in the opposite direction of its gradient, right? And that has the same effect. we have g right here. Before, it is equals to 3. After we slightly nudge our parameters in the opposite direction of our gradients, we slightly reduce g. Alright? So, what we're doing right here is we have functions, we have their variables, we find derivatives, and we decrease the function. We know that our loss function is a function of our parameters in our neural network. Could we do the same process that we're doing right here for our loss function? And the answer is, well, you can't, essentially, right? I've written it. Not only is it not actual code, because it would take too long to write, right? This does not follow our current implementation of LP. It is too computationally expensive, and it's too impractical to write, okay? So, the same thing as before. We define our MLP, right? It is a function of our inputs and all of our weights and biases, right? So there's a bunch of more things right here that I've omitted. Then we calculate we set values for each one of those weights, right? So there'd be a lot more lines over here. Then what we do is we calculate the gradient for each one of our weights, right? We have right here the loss function. The gradient of the zero weight of the zero near or the zero layer is just going to be this, right? It's going to be slightly increasing the loss minus the normal version of the loss. And then you get the gradient for the first weight. And then you have to do that for the second weight. And then you have to do that for the third weight, and the fourth weight, and the fifth weight. It's like 50 parameters in total. That's too impractical. It doesn't work out, okay? And then you slightly nudge each one of those parameters, and you would expect our loss function to go down, right? This is too impractical to do, okay? But it's good. We now know that we can use derivatives to influence our weights in ways that we want to decrease our loss function. That's better, all right? So we still cannot answer this question, but we're getting closer. Just a couple more insights, all right? So turns out there is a different way of achieving what we're doing right now, of finding our derivatives, right? And this way is called backpropagation, all right? So at the core of neural networks lies this backpropagation algorithm that allows us to find the derivatives of our loss function with respect to each one of our parameters in a way that's not that as cumbersome as what we had before. Okay? So, to understand backpropagation, what we're going to do is we're going to look at a simpler example. Not the full expression, the whole MLP equals all those variables that we had from before. A simpler expression. Alright? Let's see that I have this over here. So, A equals 2, B equals -3, C equals 10, D equals AB, E equals D plus C, F equals -2, and then we have our loss at the end, which is equals to EF, right? We want to reduce our loss. So what do we need to do? We need to find the derivative of each one of our variables with respect to the loss, right? We'll keep track of an expanding expression graph over here in the course of the next slides, so that we can apply backpropagation, right? So quick question, what is the derivative of L with respect to L? It's 1, right? So that's the first step. So the derivative, I'm going to put the gradients essentially below over here, right? Derivative with respect to L of L is 1. So next up is, we know that L is E times F. So what is the derivative of F? Or the derivative of L with respect to F, right? Well, we know that L is equals to EF. The derivative of EF with respect to F is just equals to E, which is equals to 4. So we can take this 4 and we can put it over here on the bottom of F, alright? Next up, we want to find the derivative of L with respect to E, okay? So once again, derivative of EF with respect to E, that's equals to F, that's -2. So we put -2 over here, alright? Let's expand our expression and now find the derivative of D, or the derivative of L with respect to D. And notice over here, what do? We apply a chain rule, alright? So, notice that the derivative of L with respect to D is just equals to the derivative of E with respect to D, right? This derivative over here, times the derivative of L with respect to E, which we already have. We just found that out, right? So it's -2, right? So we just expand that expression, derivative of D plus C with respect to D, that's just 1. So really the derivative of L with respect to D is the same as the derivative of L with respect to E. So we backpropagate the gradient from E to D. So that's -2. Same thing happens with C. It's the same chain rule again, right? Derivative of L with respect to C is just going to be the chain rule, right? Derivative of E with respect to C times the derivative of L with respect to D, right? Once again, this right here is just 1, so really the derivative of L with respect to C is just the same derivative that we had for E, the same gradient. So also that gradient flows back. All right? Let's finish this. Let's finish this entire expression. So we know that D is the multiplication of A and B. All right? So once again, we apply the chain rule. Derivative of L with respect to A is going to be equals to derivative of D with respect to A times the derivative of L with respect to D. Derivative of this term expands to AB, which is equals to B. So notice right here that when we have a plus node, sort of like this gradient just backpropagates normally, but when we have a multiplying node, we take this gradient and we multiply it with sort of like the opposite pair, right? So -2, we want to find the gradient of A, it's sort of like this -2 multiplies with B and then becomes the gradient of A. Alright? And then in a similar fashion, if we want to find the gradient of B, we sort of like take this -2, multiply it with A, and then we have the gradient of B. So that is backpropagation. Notice that by the end of this process, we have found essentially all gradients of this expression through backpropagation, through this application of the chain rule. And this is good, because doing code for this is much more practical. You can do less copy-pasting, I guess, by doing this process in code. Okay? This right here is just an illustration to show exactly that notion, right? We start with L, and over here we have a times node, so it's kind of like 1 multiplies with F to become the gradient of E, and 1 multiplies with E to become the gradient of F. The value of E, that is, not the gradient, of course. And then we have -2 sort of flows equally because we have a plus node, so kind of like -2 passes through, and then here that same thing, -2 multiplies with the value of B to become the gradient of A. Same thing over here. So that is backpropagation. We're backpropagating gradients, doing an application of the chain rule such that we can find the derivative of every single variable in our expression with respect to some initial term. Okay? That is backpropagation. It's not something invented by AI or anything else. It's really just derivatives from math. Okay? But we can use it. We can dispose of it in our neural networks. But first we need to actually code backpropagation. Alright? So, what I'm going to do right here is I'm going to create a data structure that keeps track of these expression graphs and keeps track of the gradients of each one of these terms in these expressions graph. Right? A data structure. What is that data structure going to be called? It's going to be called value, right? So every value object is going to be holding initially just a simple little piece of data. Okay? And we can create value objects like this. This right here is just a REPR, stands for representation. This right here is just like whenever you print a value object, what string does it output? That's it. So it's just purely cosmetic, alright? Purely cosmetic function. So let's code this value object right now in value.py. Value.py. We're going to say class value, and I do think that I do need one import. No, I don't. So anyways. So we're going to define the method, takes in self, takes in some sort of data, and then we say self.data is equals to data. And then let's just create the representation. Self, return an f string of value, and then I think I do self.data equals, this is just a special Python syntax for doing things like that, so I think this is pretty good for now. Yeah. So this right here is our initial value object. How do we actually dispose of this? Let's go to main.py. I'm just going to get rid of all this, honestly. So from value import value. What we're going to do right here is say a new value object, a is equals to value of 2. And this is how we can use it. So we can just print that value object right there. Okay? So let's do python main.py. God damn it. Okay. So there we go. So we just created a new value object. Very, very simple to start with, right? But what we actually want is we want to be able to start creating expressions. So say that I create another value object, right? What was my value for b again? I think it was -3. That's right. So let's say I create another value object, and now I want to create a c, which is a times b, right? If I do this, Python is going to freak out. It doesn't know what to do when you multiply two value objects. The operand multiplication is not defined for value objects. So we need to define that, right? Let me just show you that. There we go. It freaks out. Doesn't know what to do, right? Turns out that in Python you can implement methods for multiplying different objects. So the way you do this is essentially with this underscore add method over here, right? So we put this inside our value class, and it takes in self and it takes in other, which is kind of like the other value object. And then we say, well, whenever this multiplication over here happens, we want you to return a new value object whose data is the multiplication of the self.data times other.data. All right? That's exactly what we do over here. We return a new value object. This is the addition, of course, of self.data plus other.data. All right? Same thing for multiplying. I'm going to copy these two methods and put them over in value.py. And this should give us, let me see, value.py is going to be over here. This should give us pretty good functionality for starting to build our expressions. So not full functionality, there's probably more that we need to do all kinds of expressions that we want, but for now this is good enough. So we can essentially just copy this new version of it. So this right here is that expression that we have from before, right? A equals 2, B equals 3, then we do D equals A times Z, same thing, right? And we have our loss at the end. Pretty simple stuff. We want to print our value of L. So let me just copy this, go to main, and then liter plus paste. Delete that. So that is main. We have defined all those add and multiplication methods. Hopefully, let's cross our fingers to make sure that this works. There we go. So that is the value of L. So right now, we're able to add value objects, and we're able to multiply them. Pretty basic stuff so far. All right. What we really want, though, is for a value object to go forward, to keep track of these expressions and these gradients, right? We want, for instance, the value object L to know that it is a child of ENF, and specifically a multiplicative child of ENF. We want the value object D to know that it's a child of AB, multiplying those two. Same thing for E, right? So we're going to be modifying our value class to make sure that we can keep track of these expressions, okay? So, couple of new parameters. Might look like a lot, but it's really not. Every value object, when it's initialized, gets in some data, also gets in a set of the previous value objects that came before it, that essentially form its expression, gets an operation string, right? So this could be either a plus or a times, something like that. And I've just added this label, which is purely cosmetic, for drawing these expressions using a Python library called Graphis, which we're going to see in a second. All right? So, self.prev is really just a set of prev, self.op equals op, we just assign those values, and we also keep track of the gradients. Initially, the gradients are going to be set to 0, but hopefully with backpropagation implemented, each value object is going to store its correct gradient. Okay? So let's go over to our value object. Let's modify that real quick. So we're saying that we need prev, which is initially an empty set, or a tuple, I should say. We need op, which is just a string, and we need label, which is also just a string. And then we're just going to be assigning those things. So self.prev is equals to prev, or I should say set of prev. Then self.op is equals to op, not two O's. Delete U. Self.label is equals to label. And then we also have self.grad, which is initialized to 0. That's pretty good so far, I think. That looks good to me. And then we need to now change our add and multiply methods such that when we create a new value object, which we're doing over here, we set those parameters. We set prev and we set operation. So over here, besides just giving data, we're going to make sure that each value object also has a notion of what prev is. And so it should be self and other, right? So this right here is saying, hey, this new value object, it is a child of self and other. What operation was it made from? I should probably just do this. A plus operation, all right? And then the same thing over here for the multiply method, but of course, instead of plus, we're going to be doing multiply, all right? So those two simple modifications to the value object should allow us to keep track of these expressions. Let me see if I made any other mistakes. I think we should be all right. So right now, with this right here, I should be able to, for instance, do this entire expression, and then by the end, print what L is, print its previous and print the operation that made L. Okay, so let me go to main, visualize g delete, plus space. There we go. GG delete that. So we just run this code, see if it all works. There we go. So I probably made some typo over there, but anyways. Now we have our L value object. It has the data that it outputs. It knows from which value objects specifically it was created from, and we know that it was a multiplication. All right. Next up, yeah, this is just what we did right now. I've included a draw.py script in that GitHub that I've shown you guys in the beginning. It uses a library called graphviz to draw these expressions. I'm not going to go through it because it's honestly not that interesting, but it essentially just draws these SVGs for us over here, right? So with it, let me see if I have it in this file over here, in draw.py. So I'm just going to copy the script. It's just a graphviz script that we get from somewhere else. Touch draw.py, come over here, go over to draw.py, leader plus base, come on, leader plus base, there we go. And then from here, now with this draw script, what I'm able to do in main is we have that expression same as before. I'm able to from draw import a function called draw, and then I'm able to call draw on L, and that generates an SVG of this entire expression. Because they're going to get quite large, we want to be able to make sure we have good visualizations for them. So Python main.py, if I do fay out.svg, we're going to have over here, this here is essentially the expression that we have from before. We've not assigned labels, but you can see that the last node right there is L, and then we have, I think it was E and F. Yeah, let's put some labels over here so we make sure that we know what things are. And so, remember, every value object has a label, so we can just assign those in creation or after, and the draw script uses those labels to put those labels for us. So I'm just going to copy this right here, which essentially assigns those labels for us right here, and it draws the pretty graph with all those expressions. This right here, I'm showing you guys this because it's important if you want to do anything at home. If you want to visualize these expressions, this is going to be quite useful, I would say. And so Python main.py, fay out.svg, and there we go. Now we actually have each one of those labels over there. Okay? So now we're able to keep track of expressions, labels, and all that. We need to now start tackling those gradients. Right? How are we going to fill out those gradients? Because remember, what we did previously was we set the gradient of L equals to 1, and then it backpropagated, right? L multiplied with the data of F, which is -2, became the gradient of E, which is -2. Then 1 multiplies with 4 becomes the gradient of F. We want to implement that process right now. Okay? So this is where here is just extending functionality. So it's not that interesting right now for us to cover this. I'm just going to skip it. This right here is interesting though. We're using 10H in neural networks as the activation function. So we do need this code. So I'm just going to include it over here. I'm going to copy this. So here's just defining the 10H function for our value objects. So value goes over here. I'm going to put that over there. I'm going to have to take this import and put it on the top. And so what this means, essentially, we can do 10H right now. So we go over to main, L, I can do just L.10H and then print that. So hopefully this should just work now. Go over here, Python main.py, there we go. That is the 10H of L. Remember that before that, L was actually different, right? This right here is the previous value of L, and this is L after going through 10H. So that is just extending functionality of the value object, just putting in another function that we can use. This right here is so that we can do power. Remember our loss function, we do a power at the end. We do the sum of the squared differences. So we need to be able to do power. So this right here is just another function that implements that. It just makes sure that whatever we're powering a variable object by is always an int or a float. And then it just returns the power of the data. And then basically the child of a power object is just itself. And this is just a label. So pretty simple stuff as well. We're going to take that gladly into our value object implementation, like so. And now if we come over here to main, we should also be able to do this. Hopefully that will work out. Yeah, there we go. So now we're also able to square value objects. And we keep track of all these expressions, right? If we look at, oh, actually, I need to put this before, like that. Actually, if I just do this, if we keep track of these expressions, they're all going to look nice, right? So Python main.py, fayout.svg. Now at the very end, we see that we also square that value object, right? So it keeps track of all those expressions for us. And while we're at it, I'm just going to add this other line over here. So this right here is what the add method should really look like. Because what we want to be able to do is, instead of adding two value objects to each other, we also want to be able to add a constant to a value object. So take like a is a value object, we want to be able to add 10. But Python doesn't know how to add a value and an integer together. So this right here is just a quick way of taking care of that, right? If other is an instance of a value object, then just use it. If it's not an instance of a value object, if it's a constant, a 10 for instance, then we create a new value object with that number, okay? So this right here just, again, it's just extending functionality. It's not that interesting, but we are going to just incorporate it quickly right here. So if we go to value object, then we take a look at our add and multiply method. We can change those now to these different methods over here. They look pretty much the same. We just add this line and this line over here. All right? And that should allow us to essentially go over to main and come over here to any value object. I'm just going to do that. And add a constant. So L plus 10, right? Or really multiply 10, doesn't really matter. We're able to do this now, okay? Main.py, fayout.svg. There we go. We see that at the very end, we added the constant 10 to L. So that is just extending functionality once again. Let's see what else we have in here before we get to actual backpropagation. There we go. So there are a bunch more operations that we want to be able to do with our value objects. Again, these are not that interesting, but they are important. We need to have them, right? We want to be able to negate a value object. So this method takes care of that. It tells Python how to do it. We want to be able to add a constant to a value object, because this is funny in Python. If you take a value object and you add a constant to it, we just define the method to do that, right? But if you invert it, Python freaks out, because it does. So this right here just takes care of that as well. Same thing for subtraction. Subtraction of a value object is just the addition of the negated value object, which we have just defined over here. Then we do the inverted multiplication, inverted subtraction, and we also do division, all right? Which division is just the exponentiation to the negative 1, right? So we're defining all of these operations in terms of previous operations that we have. And we're doing this for a very specific reason. We're only going to be implementing backpropagating methods for multiplication, addition, 10h, and power. Only these, alright? And so if we only implement backpropagation for these methods, and we define all other kinds of operations in terms of these methods, we'll make sure that backpropagation also takes care of these other methods. Okay? I'm just going to copy them and add them to our value object. So we'll go to value over here. Does that look good? That looks good to me. See if we're still good. Yeah. Alright, so we've just extended the functionality of our value object quite a lot. But now let's actually get into implementing the backpropagation, right? Updating the gradients, right? So here is my suggestion, right? What I want to make sure is, whatever is the most parent node of an expression, I want to give that node a dot backward function. This dot backward function, when you call it, it's going to update the gradients of all the previous nodes that come before that node, such that the gradients reflect the derivative of each and every single one of those previous nodes with respect to the node that we're calling backwards from. Alright? Does that make sense? Good? So, to do this, the first step that we're going to do is we're going to implement a smaller backward function, right? A just back. What this does is it takes in any node and it updates the gradients of just the previous two nodes that created it, or just the one node if we're talking about exponentiation or 10h. Alright? And so the idea is this smaller backward function implements just the gradient backpropagation of a single part of our expression. The large backward function does the expression all the way to the end. Backpropagation all the way to the end. And so the idea is call back over here, call it over here, call it over here, call it over here, call it over here, and then you have called the entire expression. Okay? So, what does this actually look like? Every single node is going to have this back function. Initially, oops, my bad. Initially, it's just going to be set to a function that returns nothing. All right? We're going to be setting that function once we create value objects. So, self.back gets a function. Essentially, this is like a pointer to a function that does nothing. Essentially, you can think of it in that way. Okay? So let's go to our value object. Where is value? There it is. Let's go over here into the init method, and we're going to do self.back is equals to lambda of none. All right. Now, when we create a new node, for instance here in our add method, we want to be setting that new node's backward function into some function that actually updates the gradients. I realize there's quite a lot of changes over here to our add method, so let's go step by step. So that line right there is what we had from before, right? Just making sure that other is always an instance of a value object. Over here, remember, in our previous version of the add function, we just had, instead of assigning the new value object to a variable called out, we just returned it. No. Right now, we're going to assign this new value object that we're creating, that we want to eventually return, in fact we do over here in the end, to this variable out. Then what we're going to do, we want to make sure that this new value object is able to update the gradients of the value objects that created it, self and other. Alright? And it's going to do so by calling the .back function of this out object, out.back. And so we have to actually set that function, right? So whenever we want the out object to update the gradients of self and other, we call this backward function, this little b function over here. What does this function do? It adds to the gradient of self the out gradient. And why do we add? This is important because remember, in backpropagation, whenever we had a plus node, what happened to our gradient? It just flowed through normally, right? It didn't multiply with anything, right? It just flowed through. You might be asking yourself, why are we not just assigning the gradient of self and other to be exactly equal to out.grad? This comes from multivariable calculus. Essentially, if we just assigned the out grad to self grad and other grad, we would be overwriting the gradients that could potentially be a result of other contributing nodes to this gradient. And so by adding the gradients, we're making sure that we're not resetting our gradients throughout the process, right? If you didn't understand that, then honestly, just talk to me later. It's really just a little detail. It's not that important, but that's why we do plus equals, okay? And then the final step is once we define that function, which updates the gradients of self and other, we just assign that function to the back function of out. And remember, this right here is essentially, it's initially none, but now it's not none anymore. It's b, which we've just created, right? Same thing is going to happen for mol, but the little b function for mol is going to look a little different. Because remember, whenever we had a times node in backpropagation, the gradient of one multiplied with the data of the other to become the gradient of the opposite, right? And so over here, it's just essentially the same thing that we had before, right? Check if other is an instance of value, create the new value object, define this backward function. Self.grad should be updated to be other.data times out.grad. This is just the chain rule that we had from before, the same expression. Can you see it? Other.grad plus equals self.data times out.grad. Alright? Then we set that backward function and we return out. We can essentially do this for 10 agent power 2. It's just that the little b functions for 10 agent power are going to look a little different because, well, we're applying the chain rule and we're doing derivatives, right? But if you search for the derivative of 10age, you're going to see that it's equals to this expression over here. And if you search for the derivative of power, you're going to see that it's also equals to this expression over here. Alright? But that's all we're changing in our add, multiply, tanh, and power methods, right? We're just making sure that the new value object, which we return from these methods, has a way to update the gradients of the value objects that created it by means of this little b function, which we assigned as an attribute of the class in self.back. All right? Does that make sense? Was that too much? Are we good? Yes? All right. So we're going to be updating these methods right now. I could sit here and write them. Do you guys want me to, or can I just copy them? Is that fine? Yeah? All right. So let's just get these methods over here. I believe we need to change add, multiply, tanh, and power to new things. So the ones that we just copied. Yeah, there we go. Now we have power, the new method, tanh, and we have multiply, and we have add. Okay? So now every value object is able to update its gradients of its immediate children. Not all children in the expression. Again, we have not implemented the backward function. We've only implemented back for each node. Okay? But that's still good enough. This is almost fully automated backpropagation, right? If we go to main.py and we do something like this, we create the expression that we had before and we manually call these back functions, then we're going to see that we actually get backpropagation, right? We had the expression from before. We set l.grad to 1 because derivative of l with respect to l is 1. And then we call l.back. That backpropagates the gradients to f and e. Then e has children, so we call e.back, backpropagates the gradients. And then d has children, so we call d.back, backpropagates the gradients. Okay? So let's actually see if this all works out. So I'm just going to copy this into main. We need to go over to main. So delete all that, delete our post space. There we go. So if I've not made any mistakes so far, what we expect to see is an SVG with all the gradients. Let's see if this actually works out. Fayout.svg, and there we go. So now we see the entire expression. L gradient 1 backpropagated into E, we know the gradients. So now we know the influence of each and every single one of these variables with respect to L. Isn't that great? Well, it's good. It's not great because we still need to do the backward function. We don't want to be calling these back functions right here manually, right? We want to be doing everything automatically. I just want to come over here and not even do L grad equals 1. I just want to do L dot backward, and it fills out all those gradients for me automatically. That's all I want to do. Okay? So let's implement that function. What that function actually looks like is this right here. And it may look like a lot, but ignore this first part and look at just the last part. We set the gradient equals to 1, and then for each node in reversed topo, which we're going to see in a bit what it is, we call the back function of the node. So, as it turns out, what this first part of the code here is doing is it is doing a topological sort of our nodes. Because remember, we cannot call back in any order that we want, right? We cannot come over here and, for instance, in main, and instead of calling L.back, then E.back, we call E.back first, right? That wouldn't make any sense. E has no gradients yet. It has not backpropagated from L. So we need to call these backward functions in the correct order, right? What is that correct order? Turns out that it is the topological sorting of the nodes that we have, which is this code over here, right? Now, this is algorithms. You can take a class on it if you want to learn it. I'm not going to dwell too much on it, but you need to know what it is. Okay, we're doing a topological sorting of our nodes. We're reversing that list, and then we're calling back according to that order for each one of our nodes. Okay, so that is the backward function. All it does is call back in the correct order for each one of our nodes. Okay, so we can do this. And we can just go to value, I guess, and put that over there. So I'll just put back over here. So now we've added this backward method over here. And what we can do is we can go to main. And I can just do this. And this should theoretically work. So let me just do this. Let me do an ls rmout.svg so you can see that this actually works and I'm not, for some weird reason, lying to you. Python main.py. Now we have that out.svg. If we open it, boom, there we go. Fully automated backward propagation of expressions. That's great. How can we use this knowledge in our loss function, where we want to find the gradients of each parameters and then use those gradients to update them, right? We're really close. We just got to do a few more adjustments to our MOP class. So how could we achieve this? Now we have exactly a way to do this, right? How do we slightly change our parameters to reduce the difference, right? We can perform backpropagation on the loss value that we obtain from main.py, and then we can slightly change each parameter in the opposite direction of its gradient, because we will know the gradient of each parameter, because we've done backpropagation, all right? To do this, we need to wrap our existing neural network code, neuron.py, mlp.py, layer.py, in this new value object that we created, which allows us to do backpropagation, and some other things because we need a new loss function, but that's all right. So let's actually do this, okay? This right here is the kind of behavior that we want. We create MLP, the same as we had before. We have the set of inputs, ground truth outputs, right? We create our loss function, and then let's say that for k times, 100 times, whatever, we get a prediction of our MLP of what the inputs are. We calculate the loss on that prediction, same thing as before. We print the loss just so we can know how our neural network is doing, all right? And then for each parameter in MLP.parameters, which is not something implemented yet, we'll do it right now, we want to first set p.grad equals to 0. This right here is called 0 grad. It's a very common mistake to forget to do this. And so you need to do this first, because what we do next is we do loss backwards. So we set the grad of each p in loss, essentially, to the correct gradient. And then we do a slight adjustment, right? We have the learning rate. I guess I haven't mentioned this, but this is called learning rate, LR. And then we slightly nudge each parameter in the opposite direction of its gradient, just like we had before with those simple examples. You guys remember, right? The derivative and all that. And so, and then once we do this, we repeat, right? We get a new prediction, and then we calculate the loss again. But we don't want to be updating our gradients without resetting them first, because the gradients of one iteration corresponds to the loss of one iteration. And the gradients of another iteration should not correspond to the loss of the previous iteration. They should correspond to the new loss. So that's why we do 0 grad. This right here is called a training loop. Okay? It's probably the simplest implementation of a training loop that you could do. And this is how you train neural networks. By the end of this loop, what we will have done is we will have iteratively changed each one of our parameters to reduce our loss. So what do we expect? We expect our MLP to go from outputting things that are nonsensical, random things, to things that actually we want. Okay? So that is the behavior that I want from main.py. What do we need to do to achieve this behavior? First of all, implement this parameters function. Second, make sure that our MLP actually uses our value class so that we can call loss backward, right? Loss needs to be a value object. Right now it's not. It's just a float. Okay, so let's copy this into main.py, which is going to be the new version of how we're going to be doing things. Leader plus space, like that. So create MLP, inputs, ground truth, loss, loop, and just what we explained. And then let's implement that parameters function, which is really just simple. It's not that complicated. We start from neuron.py. We say that parameters just returns the concatenation of the self.weights list with the self.bias, because those are the parameters of our neuron, right? And then for the layer, we write the same function, and we just say return a list comprehension of p. And then this is really cool in Python. I don't know if you could do this, but you can do for n in self.ns, for p in n.ps. So just take all those parameters and put them on a list. And then we do the same thing with the LMP. So really it's just that simple. It's not that hard. So we can just code that right now. So let's take this. We're going to put it in Neuron. So Neuron, where should I put this? Just here, I guess. Delete that comment. So we define the parameters function for our Neuron. Then we need one for our layer. So let's get this right here. Then we need one for our MLP. So we come over here and we do, wait, this is, no, this is good. MLP,
So, oh boy, not bad. MOP, so we put that over there. And then, just to make sure that this is all working, let's go to main and try to call MOP.parameters. Before we do all this training loop shenanigans, let's just, before we do all of this actually, just do MOP.piece, print that, see if it actually works out, equals, close brackets, close comma, that. So Python main.py, there we go, these are all the MOP parameters. I think we have 50, I'm pretty sure it said this before, but print len of MOP.piece. So yeah, 50 parameters. The newest model from DeepSeek has like 600 billion, so we're almost there, I guess. Yeah, so we've implemented the parameters function. Next step is to make sure that we wrap our things in the value object. So this is actually really simple. The only place that we need to change is neuron.py, because remember, layer.py is based on neuron.py. MLP.py is based on layer. So everything is just based on neuron. We just need to change our neuron class to start using this value object. What we do essentially is we get rid of that activation function that we had before, right? Remember we had a self.f equals np.10h. Let me show you that right now. Where is value.py? No, it's not this that I want, right? No, I want neuron.py, that's right. So remember we had self.f equals np.10h. We don't need that anymore because we can just call .10h on any value object. We've implemented that method, so we can just get rid of it. Okay? Now, every single weight is now going to be a value object. Okay? So we're just going to wrap this np.randomUniform in our value object. So we take over here and we wrap this in our value object, just like that. Same thing for our bias. All right? Then what we need to do right here is, instead of calling self.f, we remove that, remove this right here, I guess, and in the end, we just call 10h. Let's join these two lines so it looks a little nicer. Move this right here. And so this right here should honestly be all the changes, unless I am forgetting something that we need to do in our neuron that makes sure that we can actually use the value object, do backpropagation or loss, and train our neural network. Let me just make sure that this is all correct. Yeah, value object, the bias, yeah, we call 10h. That should be it, honestly. And this is training for multiple examples. And so right now, look at main, right? In main, we had this. Let me just get rid of this. So we create our MOP, we create our inputs and ground truth outputs, our loss, and we have our training loop, right? So what do we expect to happen once we run main? We expect to see a loss value decrease. If I've not made any mistakes, that is, of course. Yeah, I've made some mistakes. Oh, of course, I forgot to import the value in neuron.py, so I need to do that. So from value, import value, and that should actually do things. There we go. All right, so once we run main.py, we're going to see right here that Control-Shift-minus, that's actually not good because it's too small for you guys, right? But anyways, we can see that we start with that very high loss before that we had of 4, and then what this right here represents is, hey, look, we've backpropagated through our loss, we've changed our parameters slightly, and we slightly decreased the loss. And we do this 100 times, and by the end of it, we get a pretty small loss. We can actually see that we've sort of like hit a plateau. This is very common with neural networks. We cannot really decrease our loss no matter what we do. There are plenty of optimizations to decrease the loss even further, but honestly, to understand neural networks, you don't need all of that. You guys realize? You just trained a neural network. On one example, sure, but you just did it. You just completely built a neural network from scratch and you just trained it. Okay? Let's actually show that it learned something. Let's go to main. And let's, I guess we can print.
K is your training at docs, right?
You said what?
K is your training at docs?
Change the training epochs. You can change it here.
Yeah, that's how many points, right?
You can do like 1,000. It probably will not do much. but print mlp.i, and then by the end, we want the very last call to mlp.py to be 1 and -1, because that's what we set the ground truth to be. The beginning might not actually be that close, but there we go. So this is for 1,000. We can see that in the beginning. Oh boy, that's a lot of lines. Okay, so clear, and tmux clear history. That should work, and then that. So enter copy mode, GG, there we go. So we've seen that in the beginning, it was -1 and -0.2. We want this to be 1 and -1. And so after 1,000 iterations, we get 0.96 and -0.96. So pretty close. It's not exactly what we want, but it's much better than before, right? If these were predictions, probabilities, these actually would be pretty good, right? So this is great. We've just trained our first neural network, but it's really just on one single example, right? We want to be training it on more kinds of examples. So over here you see that we have one set of inputs and one set of ground truth outputs. What if we wanted our neural network to learn just more things, right? Well, we can do that. We'll need a new loss function for that, because currently SSE, I cannot do GD, I think, so I just need. Currently SSE takes in PO and GTO, and so what we're kind of wanting to do is create a new function called total SSE, which takes in POs and GTOs, right? Predicted outputs and the ground truth outputs that we actually want, right? And I think I've written that function in the slides, I'm pretty sure. Yeah, there it is. So really all it does is total sum of squared errors is just the sum of each squared error. So it's pretty that simple, honestly. You can just use this as your loss function, and now you can train on however many inputs and outputs that you want. So just take this loss function, put it over here, delete that, and now in main we're going to slightly change things. It's going to be pretty similar, but now we have, for instance, I want my neural network for inputs 1, 2, 3 to output 1, -1. For 3, -1, 1, I wanted it to output the opposite. For 1, 0, 1, I wanted it to output 0, 1, and then for this, I wanted to output that. This is completely random data, but you can imagine that you can make it actually very purposeful, right? What if this was the humidity, the temperature, the cloudiness of a day? And what if these were the probabilities of raining and sunshine, for instance, right? You could really just get data that is really meaningful and tell the neural network, hey, learn to output what I want. All right? With enough compute, you can actually do it. And then, of course, instead of using that SSE loss that we had before, we use total. So total loss. And then over here, it's exactly the same training loop as we had before. My bad, not the exact same, because we actually have predicted outputs this time, right? So for each input, we tell our MLP to predict it, and then we append that to a predicted outputs list. And then we give the predicted outputs to our loss and the ground truth outputs. Loss to backward, and then do that. Okay? So that is a new behavior that we want from main.py. We've already written total SSE, so let's just take this and put it over there, honestly. Let's go to main. Where's main? There's main. Delete all that. Leader plus paste. Sick. And then we can do a couple of tests right here just to see how well our neural network is doing. So for, let's do the following. For I in inputs, but I really don't want to do that. I want to be doing for I and GTO in the zip of inputs and the GTOs. I wanted to just print the I and, or actually MLP of I and GTO, just to see how well our neural network actually learned all these things. Let me see if in loss we're all good. Yeah, we're good. So clear and tmux clear history. Then we do Python main.py. As you can see, it's taking a bit longer now because we have more data for it to learn. But over here we can see that we wanted it to output 1 and -1. It outputs pretty close to that. we wanted it to output -1 and 1. It's actually pretty close. Over here we wanted to output 0.5 and 1, and it's pretty close to that. And the same thing over here. And I guess I should have probably preemptively included what the outputs were in the beginning, so I will also do that now. Let's go to main, and then just print. I guess you can just copy this and put it before the training loop, right? Like that. Clear that. Decreases the loss. As you can see, it gets pretty damn low. And in the beginning, it was completely crazy about what we actually wanted to do. We wanted 1, but it outputted -1. And then by the end of it, it actually learned our data. So that's it. You did it. You built your neural network from scratch. You trained it on random data. Now you have all the intuitive knowledge you need to understand something in, for instance, PyTorch, right? Because PyTorch does all of this training loop. Let's just see if we get a pretty good, where is it? There we go. PyTorch defines a forward function. This is not going to be great for us. There we go. So as you can see right here, this is pretty similar to what we had before, right? For each input, we set the 0 grad like we did with our parameters. We get our predictions. We do our loss function. We do loss stop backward. We do optimizer.step. This is essentially the same as slightly changing our parameters. And then this right here is just more complicated stuff because we're doing batches. But essentially the core of it, you all know, hopefully understand, if I did a good job with this workshop, intuitively what's happening in these lines. Alright? So yeah, that's pretty much it. Do we have any lingering questions right now? Any comments? Anything at all? No? We're good? Alright, well, thank you all for showing up today. Again, if you have not registered with us, please do right now. And the code is available in a GitHub repo. I'll put the link up in a bit. Yeah, that's pretty much it. Thanks guys for showing up.